All right, welcome to this week's KCS talk. Speaker, Dr. Henry Dietz. I only learned last week how to pronounce his last name. I thought it was Dietz, but he says Dietz, right? Dietz. Anyway, Dr. Dietz is going to tell you and me what we should know about what? About quantum computing. So let's give Dr. Dietz a warm welcome.
Thank you. So mic's working and everything? Hey, all right. So I'm going to post these slides, so I left the abstract on it. You don't have to read that. You probably already kind of looked at it. And if you didn't, don't worry. There's nothing there that we won't cover anyway. So let's start out talking about some basics. So how do computers get faster? Well, it's really by parallel processing. It's by having more circuitry. Moore's law is about how much circuitry you can put on a chip. And from 1965 pretty much to the current time, we've had circuit complexity increasing about 2x every 18 to 24 months. So more circuitry on the chip, you can get more things done. Parallel processing, you can get more speed. So how's that working out? Well, it's still kind of working. Just to kind of give you some feel here. So this is showing you what the number of transistors is on various chips. And you can see it's a little bit of a scatter plot here for the different processors and such, but still looking like a nice linear plot on a semi-log graph. So life is good there. And if we take a look at this other one, this is actually the top 500 supercomputers in the world. The orange there is the performance of the top machine in the world. And you'll notice it's a little bit of a step function because those are expensive machines. You don't buy one every 6 months, right? So they last for a while. The number here is the total. The number here is the number 500th one. And you can see they're all pretty much the right trend. It's been tailing off a little bit. And you hear people predicting that Moore's law is going to end any day for the last decade or so, but hasn't really quite stopped yet. It's just maybe changed the angle a little bit. So doesn't look too bad, right? But basically, what this is saying is you want to get more speed up. You break your program into n parts. You execute them simultaneously. The bigger the n, the more the speed up. And basically, you can get fault tolerance by having a little bit of extra redundancy. So yay, we can scale up as big as we want, right? Well, even if Moore's law is with us and all of that, there are some problems. So here's the new fastest machine in the world, Capitan. And this is basically 11 million cores, so 11 million separate processing elements, and costs $600 million, which is not exactly cheap. And whoops, excuse me. Let's go back here. And basically, 30 megawatts. 30 megawatts is kind of a scary number, right? Just to put this in perspective, at supercomputing last year, the IEEE ACM supercomputing conference, the big thing that everybody was talking about was how can we get nuclear reactors built faster so that each of the major computing sites can have its own nuclear power plant. And unfortunately, I'm not kidding about that. 30 megawatt is kind of an ante, is the normal number that people are talking about for a small data center, right? So this is getting a little out of hand. And that's basically pretty bad news. It means that scaling, even though we may know how to do it, the numbers are starting to get a little bit outlandish. So let's take a look at all the bad news together. First of all, we've got Moore's law is slowing a little bit. Then we have this little detail that the power per transistor, even though it's exponentially getting better all the time, it's not the same exponent as how many transistors we get on a chip. So what you end up with is the power per chip keeps going up if you want to actually turn on all of those transistors. So this is basically becoming the main limit. You're seeing that even though you can actually put all those transistors there, you can't turn them all on. Power consumption's too high. The other thing that's kind of sad about this is that if you take a look, this graph is showing you basically the performance for a single core here as well. And what you'll see is that the individual operations are not getting much faster. And every program, every application that you could ever want is going to have some portion of the application that is inherently serial. So you're limiting yourself on the speed up. It's not looking like things are very good here. So basically, how do we get out of this? Well, there's this old James Bond film, right, Quantum of Solace, Well, I'm going to turn that around. There's a lot of solace in quantum computing, right? It sounds like, hey, this may change the rules. So what is the solace that people see in quantum computing? How do they think this is going to change the rules? Well, basically, if you're lucky and we get everything working exactly the way it's supposed to, quantum computing means that you can get massive parallel processing without having massively parallel hardware. In other words, using quantum phenomena, you can actually get parallelism in a single unit of hardware with a single unit of power consumption. That's really cool. On top of that, you have this lovely feature that it may be possible to actually solve NP-complete problems in reasonable amounts of time. Basically, the complexity limits for a quantum machine are not the same as the complexity limits for a conventional machine. So kind of breaks all the rules about what we think is complicated to compute. Things like, for example, solving the traveling salesman problem becomes really cheap on a quantum computer if you can actually get them to work right. And then, of course, the other thing that's kind of neat is, in theory, the power consumption for performing 1 unit of computation, which actually gives you this exponential amount of parallelism, can actually be arbitrarily low. So your power consumption goes way down, you get lots and lots of parallelism without lots and lots of hardware. This sounds fantastic, right? And if it sounds a little bit too good to be true, well, so far that's kind of how it's been, right? So let's talk a little bit about what quantum computing really looks like. So first of all, let's talk about what quantum computing isn't, right? So quantum computing does not just mean that you're using quantum phenomena in building a computer. Every modern computer, every modern chip is using quantum phenomena for its basic functionality. It's being used basically to implement conventional logic, all right? So yes, quantum stuff is all over the place, but that's not what we're talking about. What we're talking about here is specifically implementing a different kind of computation model from what you would normally have in a computer. And we'll talk about what that computation model looks like in just a little bit. Basically, that different computation model, there's not just one choice for it. There's actually a whole bunch of different choices that people are playing around with, and some of them are easier to build, and some of them are harder to build, and as you might suspect, the ones that are harder to build are the ones that look like they're more fun to use, and the ones that are easier to build are the ones that people have had more success building, but they're not as useful. So quantum gates is basically, you'll often hear people talk about this as the quantum Turing machine model, that you can actually program this to do all sorts of things. Well, I'll give you the sad news right up front. You can't actually build a Turing machine with a quantum system, because for a Turing machine, you need to be able to have that tape that can hold data for as long as you want. That's not something quantum machines will ever be able to do, right? However, this is a relatively programmable model, and it's nice. It looks more like what we're used to. There are other models that are basically kind of dedicated hardware for solving specific problems, such as adiabatic optimization, essentially what you'll often hear of as quantum annealing. And those models are not as much the focus of most of the effort because they're very specific things that they can do. So we've got this idea of what a quantum computer is, so let's do the quick quiz. So is that a quantum computer? You can all shout out, it's fine. Looks like a chandelier, so probably, right? Yeah, okay, so that one actually is. That's an IBM Q. That's from back when they had a whopping total of 5 qubits, right? That was actually at supercomputing some years ago. Okay, how about this one? Yeah, this is like that thing from Monty Python where they were trying to identify larch trees from a distance, right? So here, you look at that and you go, well, is that a quantum computer? It looks very credible, and the answer is nope. That's actually from the TV show Devs, which by the way, good show, and let me just say, Devs is not actually talking about developers. Okay. How about this one? It looks like a chandelier, should be, right? And it turns out that one is actually Google's Sycamore, right? Okay, how about this one? And I should say this is about the size of a regular PC. Turns out that one is a quantum computer. That is actually from SpinQ. It's a Gemini Mini. It costs about $8,000, and it's got a whopping total of 2 qubits. All right? But you can have that sitting on your desk for only $8,000. No, that one actually, there are some technologies for making qubits that don't need to be refrigerated like that. On the other hand, remember I said it's 2 qubits? there are things you can get away with for 2 qubits that you can't get away with for, 100 qubits. So this one. You may have seen this one down the hall. This is something that we built. And nope, that's not a quantum machine. That is doing quantum computing-like things, but it's not using any quantum phenomena, so it's not a quantum computer either. All right? So let's talk a little bit about the differences between conventional computing and quantum computing. So what have we got? Well, conventional computing, fundamentally, memory is made of bits. And each bit can hold a 0 or a 1, and they can hold it for as long as you want, right? By the way, that's not really true when you get into the physical hardware. Are you all aware of what DRAM looks like? Yeah, DRAM, you're basically holding charge on a capacitor. Capacitors don't hold a charge forever, but that's okay. We can have them hold it for like a second, and so long as we refresh it in that time, it looks like it can hold it forever, all right? Well, at least until somebody turns the power off, right? So, well, basically, we get bits that can hang around for many, 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 many clock cycles, and every bit can be accessed by addressing. That's really a very powerful thing. You can explicitly say which bits you want to touch, and you can get at them easily. The operations that we have are the familiar set, right? AND, OR, XOR, NOT, NAND, NOR, MUX, all these things that are basic gate-level operations. And you also have fan-out. Basically, sorry about that. Basically, when you want to have the output of one gate go to more than one place, nothing wrong with that. Fan-out of 4 is very commonly supported by most gate families. Well, if we take a look at quantum computing, it's a little different. So memory is made of qubits, quantum bits, and each of those doesn't really hold a 1 or a 0. What it holds, to be very literal about it, is a probability density function over 0 and 1. Now, what the heck does that mean? Well, basically what it means is that it can hold a 0, it can hold a 1, or it can hold both of those with some probability of a 0 and some probability of a 1, all right? And the reason we call it a probability density function rather than a probability is because it happens to be a 2-dimensional function rather than a 1-dimensional function that gives you the probability, all right? When you take a look at the value of a qubit, it doesn't look like that. It always looks like a 0 or a 1 because the act of measuring the value of that qubit causes it to basically latch into a state that's either 0 or 1. But it does that with probabilities that correspond to the probabilities of 0 or 1 in the superposed state that it was originally in. And of course, values have a limited lifespan. Basically, they decohere, and if you're wondering how long is that lifespan, the answer is it's tens of microseconds these days. So it's not a long time, right? The operations that you have for gates, well, they look kind of weird, but not too weird, at least not as one that we're familiar with. Conditional not, conditional not, swap, C-swap, all of these, so conditional swap. These are things we'll talk about what these operations are, but let me give you the quick little trick on this. They have to have the property that they have to be thermodynamically reversible operations. And thermodynamically reversible operations are not things like AND gates. If you think about an AND gate, 2 wires come in, and each of them could be a 1, and what comes out? 1, 1. What kind of a cage fight was going on in there that you had 2 1s go in and only 1 comes out, right? And I'll give you the real honest truth of it. It's neither one comes out. What actually happens is the 2 that go in are absorbed, and then you generate a nice fresh new one from VCC. So basically, that's a lot of power consumption, and make a long story short, that power consumption, something like that, would actually cause you to collapse the superposed state, and you wouldn't be able to actually have both 0 and 1 at the same time. That's why you can't have that kind of gate. Does this make sense? All right. Also, fan-out's not allowed, pretty much for the same reason. It wouldn't be able to preserve that 0 energy contribution. So what does a qubit really look like? Well, it certainly doesn't look like this, but this is the diagram that everybody shows you. So I have to be one of everybody and show it to you, right? So block sphere is basically a model of what a qubit is doing. And since I'm into physical models, right? So here's my physical qubit, nice big one, right? And I'm going to be very proper about this. So what you have here is you have 2 different dimensions that I can basically move this thing around in. And you can see that this dimension here, I currently have a 1 pointing up, right? So you can think of this as being in a logic 1 state, right? So a probability of 100% that it's a 1. If If I flip this around like that, it's got a probability of 100% being 0. And if I have it at some in-between state, I basically have some probability of 1 and some probability of 0. Right? And I can, of course, rotate this other dimension without it actually changing what that probability is. So those are the two dimensions that you get on this. Right? Now, what's really happening here? Well, basically, what you're really doing is you're using two different quantum phenomena for these two different dimensions. And you can operate on those independently, or you can couple them. And those two different quantum phenomena, what you really have is their wave functions. So you can think of having essentially a complex wave function, where you've got some waveform for each of those two things, and that's really the state that you're defining. And you look at this and you go, well, how does that actually specify a wave function? And the answer is very crudely. So this shows you what one qubit is doing, but it doesn't tell you anything about how you would actually get more than one qubit doing something. So you look at this and you go, well, okay, I get it. It can be a 0 and a 1 simultaneously, but that's only a factor of 2 parallelism. Where's this massive parallelism that we were talking about? So the trick for the massive parallelism is not just to be in superposition, but to have the qubits entangled. Right? So entanglement simply means that instead of having independent probabilities of 0 and 1 for every qubit, you can have multiple qubits linked in such a way that the state of one determines the state of the other. Right? Now that sounds really complicated, but let me tell you what it really means. If I have e qubits entangled together, then instead of getting a probability density function independently for each one of those qubits values, I get a probability density function over all e-bit sequences for that. And keep in mind, there are 2 to the e of those. So for example, if it's, let's say, 32-way entangled, that would be saying that operating on one qubit is giving me 4 billion results. That's serious parallel processing for 1 unit of work, right? So this is really what we want. And I think it's fairly clear. Each qubit can hold up to 2 to e bits if they're e-way entangled. Each of those bits, by the way, is just a 0 or 1, or a probability of 0 and 1, coupled across these 2 to the e patterns, right? And one operation, as I say, gives you basically 2 to the e results. So this sounds great. Okay, so what have we got people building? What do they really look like? Well, you saw pictures of them before, but let's actually talk about what they have inside. So there are a variety of different technologies that can be used to build quantum computers. Basically, lots of things exhibit quantum behaviors. It's just you want to pick something that's relatively easy to build and control. So what have we got here? Well, first of all, IBM Condor is currently the big one. And IBM Condor has 1,121 superconducting qubits. Basically, it's Josephson junctions in a really serious refrigerator. When I say really serious refrigerator, basically has to be refrigerated to within about 1,000th of a degree from absolute 0. So this is pretty serious stuff. But 1,100 qubits, that sounds like a pretty big thing, right? If we take a look at this machine from China, and I'm not going to try to pronounce that because I'm sure I would do it wrong, 504 supercomputing qubits, not bad. China's basically right up there. Google Willow, you probably heard the wonderful claims from Google about how they have yet again been the first to show that they have a quantum machine that's many times faster than any normal machine. Well, their machine happens to have 105 superconducting qubits. Rigetti has one with 84. Fujitsu has one with 64 supercomputing qubits. They also have a different system with 10 spin-based qubits, just a different quantum phenomenon that they're using. All right? Let's talk about Willow a little bit. So I told you Willow has 105 qubits, right? Well, it turns out the qubits are laid out in this pattern. Right? So when you think about entangling a qubit with some other qubits, it would be really difficult to do things like entangle that guy with that guy over there. Right? So essentially what happens is you only get to really entangle with your neighbors. So that would mean 5-way entanglement is pretty much where we're stuck. And I'll give you the bad news. Basically, almost every quantum machine that I'm going to mention here, 5-way entanglement is as high as they go. So this is obviously one of the big things that we hope they'll get past. But let me just say, there are reasons why that might actually be a real physical limit. If you think about it, it ends up being very closely related to what people see as noise in building analog computers. So maybe it's going to be very hard to get a lot larger than 5-way entanglement. But in any case, 5-way is the max here, basically you and your 4 neighbors. And you're probably wondering, why is it 3.47 on average? Well, there are 2 reasons. One, some of these guys don't have all the neighbors. And 2, they're not all good bits. So it turns out some of these bits don't have all the links quite working, and you actually have to deal with that. You've got basically bad bits scattered throughout. The operation of one gate on one of these qubits gives you about 0.036% error. Now, of course, that's kind of a weird measure of that, because you go, well, that's really a 0.036% chance that it's totally wrong. I think that's a better way of describing it, right? That doesn't sound too bad. But think about it. That adds up pretty fast, right? I mean, all you have to do is go through a couple thousand operations and you've pretty much got muck, right? That's for a gate that has 1 qubit that it's operating on. If you have a function of 2 qubits, it's 0.14%. And by the way, I'm quoting the happiest numbers from them. This is not the average numbers, right? When they make a measurement, they have a little bit less than a 1% chance of getting that wrong. Right? So these are kind of sad numbers, and let me just tell you, these are pretty much as good as anybody's getting. This is sort of where the state of the art is right now. How long does it stay coherent? Well, as much as about 98 microseconds, which doesn't sound too bad, until you see this number, right? So you get to do about 40 gate operations in sequence before things turn to mush. That's not a very long program, right? I mean, just to put this in perspective, doing a 32-bit by 32-bit multiply takes approximately, I think it's, what is it, 1 million gate operations? So we're not really there with 40, right? Okay, so with that little disclaimer that's a little disheartening, let's talk about some of the other alternatives out here. So, well, Intel has this thing called Tunnel Falls, which uses 12 spin bits. And in case you're wondering why some of these numbers are very low, but they still have big press releases, there are 2 reasons. One, they had a big investment and they want to make a big deal out of any little success they have. And 2, different technology for making the qubits may have different properties. They may be able to scale it up better, may have better noise immunity. So it's worth doing these things. So for example, the 12 spin bits in Tunnel Falls are a little bit interesting. Microsoft's Majorana, they've made a big fuss about that, because even though it's only 8 bits, they're like, yeah, but on our roadmap, we're scaling up to millions of qubits, right? And you go, well, you're at 8. It's a little overstatement, isn't it? But let me just say, why are they making statements like that? Because their 8 qubits are really good qubits. They think. They haven't really tested them enough yet. But they look like they might be really good. You can see, 56 trapped ion. This is yet another way of building qubits. 36 trapped ion for these. By the way, in the online slides, these are all links that you can follow, so you can actually find out more about these. SpinQ has up to 20 supercomputing bits in their machines, and then they have these little things that are just 2 spin bits that are actually read with an internal NMR that's actually reading the state. So all of the things that I've talked about here, let me just say, are in the category of essentially qubits are fixed. So a qubit is in a location, and you normally have this model that you think about computers as bits run through gates, right? That's not how these work. How it really works is a bit in a fixed location. A qubit is in a fixed spot, and you're basically pinging it with energy in some form to cause it to change state. So the gate actions are really actions taken on the qubit in place for all of them that I've talked about so far. That's not the only way to do it, though. It turns out that you can do some interesting things with photonics, and by interesting things, I mean mostly you don't need the stinking huge refrigerator, because photons are not very sensitive to interference. So essentially, there's some potential for scaling up on these. You'll notice that, you'll notice that these happen to be happily devoid of any numbers for how many qubits they are. That's because I couldn't find reliable numbers for these, but they're saying a whole lot, and they're holding big wafers, so I guess we should be confident, right? So at any rate, make a long story short, this is another thing where any day now you could have a big development, or it might take 30 years before we have something that's really a big development. Okay. You also have things that are not as programmable. Remember I was saying that there's this general purpose gate model. That's what all the things that I've talked about so far are. And then there's also these other models. And basically, the one that has been the biggest success in terms of number of qubits is D-Wave. They've got a 5,000 qubit, well, notice 5,000 plus. It's more than 5,000. It's supposed to be like 6,000 if they're all working, but again, they're probably not all working, right? So they've got 5,000 plus qubits, and adiabatic quantum annealing. What the heck is that talking about? Well, basically, you get to program this system with essentially waits for a traveling salesman problem and have it just kind of essentially in the analog domain level it out so that it figures out the optimal path. Make sense? So it's not a generally programmable thing, but on the other hand, that's a pretty important problem and pretty good if you can solve that. And this is starting to sound like a pretty large number, but let me say in reality it'll handle up to something like 15 by 15 problems, so it's not really that big. There's also limited precision, so you may have some things where maybe it just gives you an estimate of what the solution is, and then you can check that out on a conventional computer. And you'll see this sort of mechanism for most things in quantum computing. It's very rare that a quantum computer just gives you the result. Usually what it does is it gives you something that is a narrowing of the search space so you can then confirm the results with a conventional machine. All right? Xanadu is another machine fairly recently in the news. It uses boson sampling for implementing photonics. Actually, my personal favorite, and this is actually linked in the slides here, there's a woman who actually built this one qubit photonic system that basically you can see the whole machine here. Not very programmable, but it is actually a quantum computer. All right? So there's also the not quantum stuff. So I'm only pointing at mine here, but let me just say I'm not the only person who has realized that entangled superpositions are the big deal. And if you can come up with another way of operating on entangled superpositions that doesn't use quantum phenomena, that's fine too, right? So the thing that I've been pursuing, just to give you some idea, basically, it does implement entangled superpositions. It does not simulate a quantum machine. It just implements efficient operations on entangled superpositions with the same kind of logarithmic cost that you have in a quantum machine, but what it does it by is using symbolic computation. Let me put it to you this way. Entangled superpositions have very low entropy, which is a fancy way of saying you can compress them. So if you compress the representation and then you operate on the compressed form directly, you can get an exponential reduction in the amount of work you need to do, the amount of power consumption, et cetera. That's what I'm doing with the parallel bit pattern computing. Where am I at on this? Well, I've gotten up to 1,024 plus bits, 32-way entangled, which is way more than you see on these quantum machines. And let me just say, 10-way, 1,024 p-bits on a $3 micro, and I will pass these suckers around. So here they are, battery-operated $3 micros. This one is doing a standard quantum algorithm to add numbers, and this one is doing a not very standard quantum algorithm, but a quantum algorithm nonetheless, to do prime factoring. 10-bit numbers being prime factored. So I'll just pass these around, and hopefully they'll, whoops, I think I turned the power supply on one. Yeah. All right. So make a long story short, quantum isn't the only way that we can go, and I'll just kind of give you a sneak peek as to the final conclusion here. Even if quantum computers never really work, it still is worthwhile investing in looking at them, because the kinds of algorithms that people have been developing to run on quantum computers, even though they haven't had the quantum machines to be able to run them, people have been able to look at those algorithms and figure out new ways of mapping those into conventional hardware that gave you higher performance than any conventional algorithm. So quantum computing has already been a win, even though we don't have really good working quantum computers. All right, with that, let's get into a little bit of nitty-gritty. How do you actually use these things? So these are our good old friends, the usual gates that you talk about in conventional computing. And as I said, the bad news is that the inputs are absorbed, and then the output is generated anew from VCC, so there's a lot of energy being wasted in that. But on the other hand, that actually allows it to drive multiple inputs. So every output can actually go and be fed into the input of multiple gates, right? This is not the gates that we're going to be using in quantum computing. So what do we have? Well, basically, the first ones that we're going to talk about are Pauli gates. And Pauli X is the one that I think is easiest to understand. Basically, Pauli X is saying, I'm taking this dimension, I'm just doing that. Does that make sense? And Pauli Y, in case you're wondering, is flipping this dimension. Right? And Pauli Z is a little bit harder to show because it's kind of a fake if you look at that on the 2 dimensions. But basically, just simple rotations. These are gates that operate on a single qubit. So qubit comes in, qubit comes out. Everybody with me? Now, is that really what happens? No. What really happens is this is showing you the time sequence of applications of energy that create those gate actions to each of these qubits. So each line as being 1 qubit, and these things that you see imposed on that are basically at a point in time you're doing this thing to cause that gate action. Time goes from left to right. Although they're reversible, so you can actually flip it around. And in fact, it's very common in quantum algorithms that you use the fact that you can basically reverse any operation. So you can recover old inputs and things like that. All right. So these are kind of boring. So let's look at some gates that are a little bit more interesting. So here's a controlled knot. And let me just explain how this works. So we've got 2 lines. So this is a function of 2 qubits. This is the one that is being controlled. This is the controlling bit. Now, even though you don't have fan out, the qubit is still physically there over time. So you can actually use the same qubit in a series of gates over time. All right? The catch is this bit is passing through here unaltered, but the state of that bit is being used to control this. So basically, the way that this works is you can see it's a controlled knot. So if this bit is a 1, then it flips this bit. Does that make sense to everyone? And if you're wondering how the heck is that reversible, oh, it's really easy. If you think about it, if you fed it through there again, you'd reverse it. It's its own inverse, right? Because this bit hasn't changed, so it recorded the state change here, and when I flip that back, I'll get back to my 0 if this was a 1. Right? Yeah, so this is flipping in the x direction. So basically, pretty straightforward. You'll find actually most of your standard gates are just dealing with the x orientation, right? The top input, as I say, is the control. It passes through. The bottom input is inverted, right? Both inputs can't be the same qubit. Why? You can never have fan out, right? And in case you're wondering, how do you get away with that? The answer is you make copies. If you take a qubit and you make a copy of it, then you can actually have those 2 bits used in different places. But make a long story short, you can't reuse a qubit directly as input to more than one place in a gate. And if you think about what this gate functionally does, it's basically the same as an exclusive OR. Yeah? Yeah, so the way you make a copy is you don't really make a copy. What you do is essentially you use 1 bit to control another so that you get another bit that has the same pattern, but it costs you an extra bit. So it costs you an extra bit and it costs you some operation. But and actually there's a name for those extra bits. If you're talking to quantum computing people, they're called ancilla. And if you're talking to normal people, they're called garbage bits. Yes, that's right. You're making it happen to have the value that you wanted. All right, so that's C naught. Okay, the next one I want to talk about is called a Toffoli gate, also known as CC naught, conditional knot. And you can see basically it's got 2 bits that are passing through, and both of these have to be a 1 in order for this thing to get flipped. Does that make sense? So pretty powerful little function, right? Next one we've got is swap. And swap sounds really kind of insane because you go, wait, there's no control here. What is this doing? The answer is it's flipping these 2. It's saying what came in here goes there, what came in here goes there. So why is that of any use? Well, if you think about it, the operation of assignment, A equals something, is not an okay operation. It's not something that preserves the reversibility. So this is a reversible assignment. Right? So for example, if this is a value A and this is a value B, and I want B to be assigned to the value of A, then I can run it through this thing, so I essentially get the value of A swapped onto qubit B. Does that make sense? A becomes B, right? So it's an exchange, right? All right. Then we've got the Fredkin gate, which is one of my personal favorites because Fredkin gates are what are called billiard ball conservative. In other words, if you count each logic 1 is a billiard ball coming into the gate, the number of billiard balls coming in and the number of billiard balls coming out is equal. So it's obviously conserving energy there. But basically what you've got is you've got this control, and what it does is it says if this is a 1, it swaps these. If it's not, then it doesn't. Pretty straightforward. And let me just say, remember, multiplexer is a universal gate. This is a superset of a multiplexer, so obviously you could build any arbitrary computer logic with nothing but these. Right? Okay, so let me just back this up a second here. Right, so basically everything we've talked about here looks kind of like conventional stuff. So how do we do anything more interesting? Well, there's this funny little H gate, right? So this is where we start doing something interesting, right? So what a Hadamard gate does is basically it takes something that is, let's say, a 0 value coming in, and what it does is it turns it into a superposed state that's equiprobable 0 and 1. Does that make sense? So this is how we go from a conventional logic value of 0 or 1 into something that is a superposed state. And if I have a Hadamard operator across multiple qubits, then basically it produces the equiprobable distribution of all the values that you can represent in that many bits. How is that reversible? Because basically it keeps track of, remember you've got 2 dimensions, one of them that doesn't affect the value and stuff. It keeps track of exactly how it split it, so it actually is its own inverse. You can think of it as doing a rotate of 180 degrees, and when you rotate another 180 degrees, you get back to the original. And I know that seems very counterintuitive, but almost everything about quantum computing feels kind of counterintuitive. The key point is, though, this is the way that you get something that's entangled and has a distribution like that.
So, sorry, does that look like an H with E inputs and E outputs, or is it E H's?
Yeah, so ideally it should be an E input H, all right? And again, you're not seeing E being high enough for it to make a whole lot of difference these days. But yeah, so basically, yeah, it gives you the equiprobable superposition. And let me just say, this is telling you another one of the big problems with quantum computing. You'll often hear people, especially physicists, talk about this, and I actually did this at E-Day myself, talk about quantum computing as, oh, well, like for example, if you wanted to solve a maze faster, just follow all paths simultaneously. Yeah, parallel processing could do that easily. Quantum, not so easily. Why? How would you initialize one of these entangled superpositions to be the representation of the maze pattern? Turns out that's exponentially hard. So that's not so great, right? So let me just say, this is actually a bit of a problem. Makes it great for doing things in number theory because then you're looking at all the values. Makes it kind of hard when you're having empirical data that you want to process, all right? But the cool thing is, again, if I do this, right, I get this equiprobable E-way entangled superposition. And come on here. Yeah. And if I operate on that, right, basically this is where I get my parallelism. So 16-way entangled, every time I do a gate level operation on one of these qubits, it's operating on all 65,536 possible 0 or 1 values, the probability distribution over those, for each one of the values in the superposed state of that one qubit. Right? So basically what you're getting is this huge amount of parallel processing without parallel hardware, without the power consumption being magnified, et cetera. So this is the huge win. All right? Now, this allows me to operate on a superposed state, but how do I look at the superposed state? Well, the answer is you can't. Right? So what you can do is you can do what's called measurement, and basically the act of measuring it collapses the superposed state, And what you get is a single 0 or 1 for each qubit, but with the probabilities corresponding to the probability distribution for that. So the probability that you get a 1 is the probability that 1 appears in that probability distribution that it had in superposition. So if you sample it many, many times, you can actually build up a representation of what the probability distribution was.
Why are there two outputs?
Yeah, so, so think of it as 0 or 1, okay? So it's basically getting it into a fixed state. So what's really being represented here is the fact that it's no longer in superposition. So you have something that's a potentially superposed state on a single qubit, and what you end up getting is basically, is it a 0 or is it a 1?
You're not getting qubits out.
Well, you can think of them as qubits, but they're qubits with a conventional state, not a superposition. All right? So, yeah, they're conventional bits is the best way to think of it. So you only get to read one answer per run. So most quantum computers, hey, they're noisy anyway. You want to do multiple runs to get a reliable answer. You're going to be doing lots more runs because that's the way you can actually sample the output space. All right? Okay, so. All right, so let's just show you a very simple little example. Here's a 1-bit full adder done as a quantum machine. All right? So, well, basically, what are we doing here? Well, I have P and Q are my two inputs to this 1-bit adder, and here's my carry input for the 1-bit adder. And you look at these guys, and you go, what the heck are they? And the answer is they're ancilla. They're extra bits that I need because of the way that these operations work, but they're not actually doing anything useful, right? They're just allowing me to use these reversible logic gates to perform the computation. So I have this stuff come in. It's going through these gates, which you may recognize as C-swaps and so forth. Basically, actually, all of these are C-swaps, right? So all conditional swaps. And here's what I get out. I get basically P and Q both come out unharmed, so I can still use them for other things. And then the carry comes out as the carry resulting from this. And the parity comes out as basically the lower bit of the sum. So your 2-bit sum is coming out here. And what is this bit? That's garbage. All right? Okay. So pretty straightforward. Just to show you, using a simulator that is based on the stuff that I've been building here, this is just running a little version of that through here. So you can see I'm setting up my bits here, and I'm running through these C-swaps. And this is showing you, out of 64 possible values in this machine, how many of them have each of the values. And you can see it's pretty straightforward. It's basically every place it's either everybody's got 64 or 0, except for this bit because I'm not using it. This is only using 5 qubits. This is a 6-qubit simulator. Does that make sense?
No. How are we supposed to read that?
Yeah, so what you're seeing is this is telling you for each of these values what the probability is a fraction out of 64 that it's a 1.
And the time goes down.
So time goes down.
Okay.
All right? So basically it's, so the normal way would be to write it sideways, but I'm doing it this way because that's easier typographically. All right?
So G is your constant 1, and you're not sorting times 0?
Yeah, so the stuff that I have here, these are the inputs, and the parity is actually the other input that I had, right? And it gets overwritten in the end with this other thing. So this is what you get as the output, and it's 100% that that's what you get, which is what you'd expect because nothing here is in a superposed state. So let me go to the next one here. All right. So let's give it something with a little superposition. So I'm going to let the carry be both 0 and 1. So that question mark there is my Hadamard operator. All right? So now what I get is the carry has a 50-50 chance of being a 0 or a 1, 32 out of 64. And what I get is when you go through this, basically I get 50% probability that I've got the answer is this, which would basically be 0, 1, in other words 1, and 50% probability that it's 2. All right? Now, that's fairly interesting, but let me just point out, we can be wild about this. Let's make them all. So we're literally going to do every add that you could possibly do, all in one shot, and what you get is this probability distribution of all the different values. And again, the same execution time, the same logic. This is the exact same thing. So here you can see we're getting our parallel processing for free, right? Now, what I've shown you there was my programming model version. So let me show you some other ones. So IBM Qiskit is a very commonly used. This is probably the #1 quantum programming environment that people use. And you can see it's pretty straightforward. So here I'm saying, OK, create a quantum circuit that has 2 qubits. Then it's doing a Hadamard operation on a 0. A Hadamard operation on bit 0 out of those 2 bits, so the first bit. And then here it's doing a controlled NOT on bit 0 and 1. All right? And then here it says, OK, draw the actual diagram that shows what this is. And of course, you can go through and have it simulated or run it on a real IBM quantum computer via the web. This is basically what the circuit looks like. So these are both starting at 0. It goes through a Hadamard gate that makes this equal probable 0 and 1. And then basically, it conditionally flips this. So this is going to be equal probable 0 or 1 when we get to the result. Pretty straightforward, right? So you get a little bit of a feel for how this is programmed. And let me just say, bit level, right? You're literally saying exactly what happens to each individual qubit in quantum programs. Okay? Another one, Q-sharp is what Microsoft is pushing as a little bit higher environment for this. And you can see it's fundamentally very similar. So what you have here is it's saying, OK, give me a qubit, then do the Hadamard operation on it, and then sample the result of this, and 50-50 chance that I get a 0 or a 1 on this. Does that make sense to everyone? OK, just to show you what I've been doing. So I actually have a C++ environment that basically allows you to write quantum programs like this. So this is actually the little 4-bit quantum adder that I was passing around on that one microcontroller there. And you can see how it works. So p-bits, basically, you're just declaring these. P-bit is qubit, basically, pattern bit, right? So this is declaring a pattern bit named A0 that is initialized to 0, et cetera. And then you can see the Hadamard operations on these, although you have to give the dimension that you want the Hadamard function to take place in. And I'm not going to explain that. Let me just say it's not simulating quantum, right? It's doing entangled superpositions, but it's not quite the same. So there's the difference. You have to specify some extra information. But otherwise, you can see this is basically all the same kind of operations that you would have on a quantum machine normally. The interesting thing is I also have pattern integers and, in fact, even pattern floats. So you can actually write things like, for example, this code here is a really sick way of computing the square root of a number. It's basically give it a number as an ordinary integer, and then what it does is basically it generates all the things that could be essentially square roots of that, multiplies them all to multiplies each pair together to see which ones actually end up being the square root, and then that's the one that it tells you is the result, right? Kind of silly, but hey, kind of impressive, right? This one, by the way, is what was running on that other little $3 microcontroller I was passing around. So this is actually doing prime factoring. And it's a very similar thing. What it's basically doing is it's factoring these numbers by essentially creating all possible things that could be multiplied together and finding out which ones of those, when multiplied together, give you the thing that you were trying to factor. Very straightforward algorithm, pretty clean. All right, so let's talk for a little bit about this quantum supremacy or quantum advantage concept. Where do you actually get a plus out of this? So these are various companies who have claimed at one point, well, I guess not company, but at any rate, various entities that have at one point or another claimed that they have been able to demonstrate quantum supremacy, that they could do something much faster than any conventional machine could do it. And you can see it's been progressing, right? Basically, the question is, what does that mean? Well, the definition of quantum supremacy is officially that you're solving a useful problem faster than a classical computer could. All 4 of these are able to solve problems faster than a classical computer can. The catch is the only problems that they've been able to solve faster than that is simulating themselves. So basically what they're doing is they're simulating themselves, including their error model, which is actually more difficult for a real computer to do because they don't make errors. So you have to actually do double precision floating point arithmetic to, I'm not even going to get into it. So let's just say, are these really valid claims? Not really, because they're not really useful. So for example, Google, for their stuff, has been pushing random circuit sampling. Random circuit sampling is literally just running through a sequence of operations and looking at the result. And that's not really something that we would have a hard time doing, because I can even symbolically tell you the result without doing the computation. It takes order constant time. So the stuff that they were saying would take longer than the universe has existed on a conventional supercomputer. Yeah, you can do it in the compiler at compile time. All right, so at any rate, that's kind of depressing, but what is quantum really good for? Well, basically, if you have a problem where you need to try all possible values, you don't need all answers, you just need one or some of the answers. You don't mind occasionally getting wrong answers. In other words, you're going to check the results and repeat it if it's suspect, which, by the way, is a perfectly reasonable thing to do. If you're trying to do things like prime factoring, just being able to filter down the search space is a huge deal, right? So that sounds terrible, but that's actually quite reasonable. And in fact, that's actually where an awful lot of these algorithms that were designed for quantum machines and then translated over to conventional machines have won, because people didn't think about doing things that way, where you would get an unreliable filtering and then basically check it and find out, oh, wow, that was quicker than doing the whole search the regular way. Combinatorial logic operating on few qubits. Why combinatorial logic? Can't build a state machine. Can't hold values arbitrarily long, can't build a state machine. So quantum computers aren't really a thing. There'll never be a quantum computer that you can run Microsoft Word on, all right? What you really have is quantum computers are basically these very special purpose accelerators that you can hang off a conventional computer. And when people like, for example, IBM are talking about a quantum computer, they're really talking about, they have this quantum chip that's inside of this refrigerator, et cetera, and then they have basically a couple of racks of standard computer that's really running it, controlling it, and actually doing most of the computation. All right, so in conclusion, quantum computing is a way past Moore's law. Definitely, it absolutely can do this, but only for very specific kinds of computations. There are very strong constraints on what you can do on a quantum computer, and basically nobody's saying those are going to change, right? Those have to do with the fundamental properties of the system, right? Quantum computer hardware might never get there. You might never see quantum machines with large numbers of qubits that work reliably. However, I would claim that that doesn't matter. It's kind of a Pascal's wager sort of thing, right? The benefit for quantum computers working, if we can get them to work, is so high that it justifies a fairly high expense trying it out. On top of that, we've got this consolation prize that even if it doesn't work with a quantum computer, we may have come up with new ways to build algorithms that will let us do more efficient things on conventional machines. And that has been true for everything that people have tried to prove quantum superiority with so far. Just to put this in perspective, you often hear cryptography is going to be broken by quantum computers, right? Well, just to put that in perspective, RSA cryptography uses 2048-bit keys. You're not even seeing 2048 bits in pretty much any of these machines yet, right? We don't have that many qubits. Shor's algorithm, which basically is a filtering algorithm, it actually runs primarily on a conventional machine host and just does quantum steps that essentially give it filtered guesses trying to reduce the search space, right? Shor's algorithm, it turns out, would need something between 1 million and 10 million qubits to be able to be implemented such they could break RSA cryptography. Yeah, so if you think about it, it would obviously need to have at least something like 2048, right? And there's basically another factor of at least 1,000 to try and actually make the qubits reliable. And again, this is why you see these different technologies being used, because that factor of 1,000, it might be a factor of 1,000 for one type of qubit, and it might be 10,000 for another. But basically, you can see we're not there yet, right? So I think just, to kind of quickly summarize all of this, I know this is a little bit depressing from the point of view that, we were perhaps hoping that quantum computers were going to save us all. Quantum computers probably not going to save us all. But on the other hand, thinking about quantum computers has been doing pretty well so far. And who knows, we still have a shot that maybe it will change everything. And, will your programming background and such be wrong? No, because most stuff is still going to run on a conventional machine. But just like you offload a lot of specific things to a GPU now, you may be offloading a lot of very specific things to a quantum machine in the future. So, thank you.
Chairman Mayor. All right, we have time for a few questions. Any questions for Dr. Dietz?
So how does quantum computers or computing can change the AI world?
Okay, so how does quantum computation change AI? Well, that's a good question, and I'm sure you'll get very positive answers from the folks at Google because it's an AI group that is doing the quantum computing there. Basically, I think the key issue is that it's cheap to do things that are trying all possible values. So if you start thinking about neural network training, things like that, that looks like that might be very easily accelerated with this kind of computational model. So I think that's where most of the emphasis has been that I've seen. Is it worth doing right now? Probably not. Yeah.
Here.
By cheap, you're meaning computation time and not electricity power.
No, both. Because keep in mind, you know, if you have something that you're trying all possible 32-bit values, you're doing that with 32 qubits and 32 function units operating on them, rather than with 4 billion function units.
Which
Right.
would also take a lot of energy to cool.
Well, yeah, so let's put it this way. My machine room down the hall is, if I turned on everything, is heating half of this building during the winter, and unfortunately also during the summer, right? And my machine room has 30 tons of air conditioning. 1 ton of air conditioning is the amount of cooling you get for melting 1 ton of ice over a 24-hour period. So think of melting 30 tons of ice every day if I had that full powered. Now let me give you the fun number. So my machine room back 8 years ago when I first noticed this horrible phenomenon was capable of powering about 1/2 of one rack in the world's fastest supercomputer at the time, which had several thousand racks. All right. So what we're really talking about here is quantum computers, yes, they're also going to get huge because to have 1 million qubits or 10 million qubits, they're going to be things that look more like stadiums than like my machine room. But make a long story short, there's still going to be, relatively speaking, modest power consumption compared to what you would have to build to get the level of parallelism that they're actually implementing. Does that make sense? So it's that exponential reduction if they can get it to work. With it being 5-way entangled, no, because 5-way entangled max benefit you're getting is 32x. Frankly, they're taking more power than that, so they're not a win yet.
Questions?
Go ahead. Go ahead.
Yeah.
Thank you, sir.
I was like
Oh,
wondering.
by the way, let me just interrupt for a second. I brought a box of qubits, so have a qubit. And no, they are not entangled. Here. No. Well, I guess you could. They're PLA, so in theory they're biodegradable, but don't try it. Yes, go ahead.
Thank you for this. I take away while going about your office a lot of time.
Uh-huh.
Yeah, so I was like, okay, the question is like when dealing with bits for like decades now, when like transmitting data, so basically when you transmit like bits of like ones and zeros, so they basically corresponds to like voltages or amplitudes of 1 or zeros.
Mm-hmm.
Now, while like transmitting qubits, will that demography change in terms of networking?
Okay, so qubits are, in most of the machines that we're talking about, the qubits don't move. All right? So to be very simple about it, it's not really a similar thing. You're not really sending any information from here to there. It's all in one place. Think of it as processing elements in memory, right? Now, if you talk about quantum communications are a little bit different, and you know, there are a variety of ways to do that. But for example, sending a photon from here to there, that's not really changed. And if that photon happens to be entangled with another photon that's here when you're sending off the copy there, cool. If the state over on that one collapses to a particular value, you'll see this one will collapse to a particular value. Basically, yay, you get to have this entanglement carried over, and you're still just sending a photon, or you can do the same thing with an electron, at least in theory. So it's not really different that way, but you're looking at a different property, and I'll give you the punchline on it, is you're not sending information faster than the speed of light when you do that, because even though when that one collapses, this one collapses, and it's apparently instantaneous, it doesn't have speed of light delays, there's no way you can actually get information out of that because the collapse is to an unknown state that happens to be the same for both of them, but
So
there's
that's
no
a garbage
information
state
transmitted.
basically.
Yeah.
Okay, so because I was like, if you consider like cloud systems, like when you do calculations on clouds, like if you want to like communicate with it, like take a state from the cloud system and then take it, then do some operations and send it back, then special things needs to be designed.
Yeah, so being able to transmit a superposed state from one place to another is certainly something that a lot of people have been working on. It's not really the quantum computing aspect, but it is in the sense that, for example, the stuff that IBM is doing now, they're not actually just doing one chip. They're trying to do multiple chip modules and basically be able to transfer state between them. But to the best of my knowledge, that hasn't really happened yet. Yeah, so that's kind of going on. By the way, for photonics, that's much easier. Photonics basically, photons don't pay attention to anything, right? So it's much easier to keep photons entangled over a distance. Yeah.
Thanks for a really nice talk. So your slide that said conventional computing should really be conventional digital computing, because we've had analog computers for longer than we've had digital computers, right? For differentiation, integration, those kinds of things. So it makes me wonder if there might be applications where things that were once computed with analog computers could be sped up or parallelized or something. I don't know if there's anything useful. Also, is there research about new kinds of gates, new kinds of operations in the quantum domain, potentially with analog implications? I don't know.
Sure. So first of all, you're absolutely right. I did keep it restricted to digital because I'm talking to computer scientists, and we tend to default to that. Or like as I tell the students in 360, our goal in this class is to not have things look analog, right? So basically, you're absolutely right. There are a lot of analog computing elements out there, and in fact, a lot of the things that are attempting to get similar benefits to quantum computing without using quantum phenomena are basically just analog computers. So there are definitely lots of similarities. It's also true that even though I was saying, for example, that these operations are turning things 180 degrees, some of the quantum machines, you can turn them by arbitrary angles. And what precision can you do that with? Well, right. So there's a lot of complexity that comes into that. There are some analog properties, and certainly, for example, the stuff that is being built by D-Wave is actually using analog properties for essentially determining the weights in that simulated annealing that they're not simulated, in that quantum annealing that they're doing. So yes, there definitely is a lot of stuff that should be coming back in the analog domain, and there is. There are an awful lot of people looking at that. As far as different quantum gates, basically different ways of building a qubit tend to have different operations be easiest. So there's a lot of investigation of what is the best thing to do with qubits built a certain way. And I'll just say, for example, we have some stuff going on. We have some DoD, I guess it's a DOE funding to look at essentially spintronics type things. There's all sorts of different gate type operations that you can think about for some of these things that don't look like the ones that I've talked about, but these are the ones that everyone is standardized on, and they're largely because the Josephson junction approach has been the dominant thing. That's what everybody's been able to do easiest, and if you ask why, that's because it's most compatible with what we do as normal VLSI fab. So, the least weird fab.
We thank Dr. Dietz for his very exciting talk.
And by the way, I'll give you the
Please,
big disclaimer too. I've now told you a whole bunch of things about quantum computing, and you should only marginally trust any of it. because like anyone else in the field, I don't really know for sure everything about quantum computing. I rate myself as an A+ on the computing side and a C- on the physics side, which makes me better balanced than most people, but still. So just be aware this is a changing field. You want to take everything here as just kind of a quick overview. Do not take it as the absolute word of God. All right.
All right, thank
So
you
thank you.
again. Thank you very much.